Hello and welcome to the channel Understanding Concepts of Physics. Hope you all are doing well. Hope your studies are going well. And we have been doing oscillations since past few videos. If you just recollect, then we had discussed about acceleration in the previous video as well as the differential equation of linear simple harmonic motion. In today's video, we are going to discuss regarding the velocity of a particle in a linear simple harmonic motion. Again, it's going to be a very short video. It's a very small derivation. Slowly and gradually keep doing this small derivations, and at a certain point you will see that you might have done a huge part of the chapter. So let's just quickly start with linear velocity in linear simple harmonic motion. So velocity in linear simple harmonic motion, if you want to derive, you start with acceleration. So I would like again to highlight that this chapter is building on one of the equations, that is f is equal to minus kx, and this f is equal to minus kx, with that you can find out the differential equation, and with this differential equation you get what is called as the acceleration. And when you use acceleration, you will definitely come to something called as the velocity, and when you want to find out the displacement, we'll be using velocity equation. So let's just see how it works. So acceleration is minus omega square x, and acceleration can always be written as dv by dt, that is the derivative of velocity with respect to time. Then I see that there are three variables aligned over here. Velocity is a variable, time is a variable, and displacement is a variable. Omega is a constant, but we will not be able to differentiate or integrate using three variables. So I'm going to reduce this into two variables. So what I'll do is I'll multiply by dx and I'll divide it by dx. So this is that step which I have done, and then I'll just move this dx on the other side. So this moves here, dt comes here, dx comes here. So this dt and dx is interchanged. Then dx by dt, that is the displacement upon time, is velocity, and dx by dv by dx mein dx is moved on the other side. So dx is moved on the other side, and just remember that velocity is nothing but dx by dt, that is the derivative of displacement with respect to time. Now at this position I am seeing that there are only two variables, so I landed up with v and x. There are the only two variables. Omega is a constant. Now I am going to integrate this on both the sides. So integration on both the sides, and minus omega square is a constant, so I have taken minus omega square outside, and integration on both the sides. So when I integrate this, since I don't know the limits, I am just not putting the limits over here. Integration of v will become v square by 2, and integration of x is x square upon 2. Minus omega square is a constant, so that is taken out. Plus there is a constant of integration that I'll call as c, and this is my first equation. Now to start with, we don't know the value of c because we are finding out v, and in finding out v we have landed up with one other constant which is c. So we are going to find out this c by using some boundary conditions. So this condition, which I have put that in orange, is what is called as the boundary conditions. So boundary condition is applicable on variables. So we have two variables in our equation, one is v and the other is x. So if you see the oscillating part of the system, if you see this diagram, then we know that the body is oscillating here, from here and there, from the extreme position. So this center position is the mean position, this is the negative extreme position, and this is the positive extreme position. So the body is oscillating between the two extremes. Now what happens is when the body actually goes to the extreme right, the displacement is maximum, and the maximum displacement is called as the amplitude. We call it as x is equal to plus a. And a very special thing happens at the extreme position, that the body actually stops momentarily. So it is going to stop. That means the velocity at this point is 0. So the velocity at the extreme position is always 0 in an oscillating body. Same when the body goes to the negative extreme, the displacement is x is equal to minus a. So x could be plus a or minus a, and the moment body actually momentarily stops, and if it stops, that means the velocity is 0. So to conclude with, whenever the body is at the extreme position, the velocity is 0. That means whenever x ka value is either plus a or minus a, that is the extreme right or extreme left, this is minus a and this is plus a, this is 0, then we say that the velocity is 0. Now this is a very logical statement, nowhere the derivation says that, but you should be able to understand that x, if it is plus or minus a, velocity is 0. So I'll put the value of x here, I'll put the value of v over here, and I'll get the value of c. So in place of v, I'll put 0, so 0. In place of x, I'll put as a. I'll move this on the other side and I'll get minus omega square a square by 2 is plus omega square a square by 2. Putting this value in equation number 1, so this is my equation number 1, and if I put the value of c in that, I'll get v square by 2 minus omega square x square by 2, and wherever there was c, I'll put an omega square a square by 2. So wherever there was a c, I have put a value of omega square a square by 2. Now it's a simple math, 2 gets cut and v square is equal to, in I can take out omega square common outside, so omega square comes outside. So what remains? So 2 is not there, 2 is not there, omega square is absent, omega square is absent. Now I am seeing that this a square is positive and this minus x square is negative. So I have taken the negative term at the second term and a square as the first term. So it's just replacement of first term as the second term. So I can write minus x square plus a square as well, but generally we write positive terms ahead. So a square minus x square. It's just a different way of writing. And then I don't want a square over here, so I'll take the root. So when I take the root, square and root will get cancelled. Omega square and root will get cancelled, so I'll get omega. And this I cannot do anything, so I'll keep the root as it is. And a square minus x square will remain as it is. Plus and minus, why? Because whenever you take a square root, you can get a positive or a negative value. That's why we get this equation. So this is what we were striving for. So velocity is equal to plus minus omega root of a square minus x square. So if the body is moving on the right side, the velocity is positive, and when the body is moving to the left side, the velocity is negative. Now this would be the end of this video, and I hope you have understood and taken notes of everything what we have discussed. You can go back and pause the video and take down the notes. In the next video, we are going to discuss the displacement in linear simple harmonic motion. So be with me and just keep following the playlist. Thank you so much for watching the video. Subscribe the channel in case you have not done so. Thank you so much. Have a nice day. Bye.